To this point in our unit, our focus has been on what happens to our bones in a collision situation. But what we haven't really analyzed, although we've made mention of it, is the effect of high acceleration or specifically high deceleration rates beyond breaking bones. In very low G environments, astronauts have been known to experience arrhythmia or bone loss. At high G levels, pilots have been known to black out. So clearly there's an effect that either low G or high G environments have on the body. Now, based on experiences of crash victims and pilots, a general rule of thumb was thought to be that the human body shouldn't be suggested to more than 30 Gs. We're going to expand on that a little bit in time, but we can take a look at a circumstance like this, where we have a passenger with no seatbelt, unfortunately, at 30 miles per hour, crashes and is stopped in a dashboard that collapses by a tenth of a meter. So we're going to see whether or not the person is going to exceed this 30 G criterion. So on a velocity time diagram, we'd be looking at a situation like this, where we have our initial velocity at the time of the accident. We end up moving to a velocity of 0 over some stopping time, and then the area underneath the triangle is our stopping distance. So as an equation, we can write our stopping distance is equal to that area underneath the curve, so 1/2 times the initial velocity times the stopping time. So the question is, what is that stopping time? Because we know the stopping distance, that's our 0.1 meters, and we know what that initial velocity is. It's this 30 miles per hour, which if we convert to SI units, hopefully this is a familiar number to us at this point since we've been using it throughout the entire chapter, so 13.4 meters per second. And so then that allows us to solve for that stopping time, which in this case, if we solve for T sub s, we get 0.0149 seconds. So with that now, we can figure out what our deceleration is, because our acceleration is going to be our change in velocity, which is just whatever speed we were driving at the time of the accident, divided by our stopping time. And so we've got our 13.4 meters per second over the 0.0149 seconds that we just solved for. And so we get a deceleration in this case of, if we round to the three significant figures, of 899 meters per second squared. And so to get a number of G's, we can divide that total by 9.81 meters per second squared. And so we end up with a count of 91.7 Gs. So that's clearly above the 30 G criterion, which can be used as a rough rule of thumb, but we can expand on further. Now before we do so, let's put a crumple zone in the car and a seatbelt on the passenger and increase our stopping distance to 0.6 meters instead of the 0.1 meters and see what happens. So our same equation, our stopping distance is equal to 1/2 times the velocity times the stopping time. So if I'm going to increase the stopping distance by a factor of 6, well, and my velocity stays the same, well, that means my stopping time is going to be increased by a factor of 6, which then means the number of G's I'm going to experience is going to be reduced by a factor of 6. So we can take that same answer that we had before of 91.7 G's, divide that by 6, and we end up with 15.2 G's, which is well below our 30 G threshold. But as we mentioned, that 30 G threshold is incomplete because what it doesn't consider is the amount of time that the person has been exposed to this number of G's. We've observed that very high decelerations on the order of over 100 G's is survivable as long as the exposure is brief enough, whereas even just a couple of small multiple of G's can be fatal if it's for a long enough period of time. So we need some sort of measurement that helps us to determine what number of G's for how much time is survivable and what is not. What we see in the graph here are some experimental data points, meaning observed episodes of individuals who experienced a certain number of Gs for a certain period of time. So that's what the dots on the graph are. Now this is graphed on a logarithmic scale. If we look at the x-axis, we've got the duration of the exposure in seconds, but clearly that's not in a linear pattern. On the y-axis, same thing. We've got the average deceleration in Gs that the person experiences, but again, graphed on a logarithmic scale. And when we put those extreme episodes on a graph, we see that they come pretty close to having a linear relationship on this logarithmic scale. And so we can find that equation of that kind of boundary line that's shown here. A equals 0.002 times the duration raised to the negative 0.4 power. You can take my word for it that that equation is accurate for that line there, where A is the number of Gs, not acceleration in meters per second squared, but the number of Gs that the person experiences, and T sub S is the amount of time of the exposure in seconds. And so the first thing to understand is that this is not a scientific law, that this equation, if you're above it, so you end up with experiencing some number of Gs for a point that ends up for a period of time that ends up above this line, that you're guaranteed to die, and if you're below someplace here, that you're guaranteed to survive. But this is through observational data, through accidents, through observing test pilots and that sort of thing, where we have this kind of boundary that seems to exist. And so we can rearrange this equation so that it is in a little bit more user-friendly format. And so we've got A to the 2.5 power, so the number of Gs raised to the 2.5 power, times the time of exposure equals 500. And so that's the boundary line, meaning that if we end up with this A to the 2.5 times the time of exposure, T sub S, ends up equaling greater than 500, then we're ending up above the line, and so therefore we're going to assume that that's not a survivable circumstance. It just hasn't been observed. Whereas if we end up below, now we've got a chance. So if our GSI, as we call it, the Gadd Severity Index, ends up below 500, then we at least have a chance. Now this is, again, not considering any kind of impact at all. This is just as a result of the deceleration. Is it survivable or is it not? Has nothing to do with any kind of impact that might happen in the collision. It's just looking at the number of Gs. So let's take a look at a couple of scenarios, calculate the GSI. So independent of any kind of impact, is the circumstance survivable based on this Gadd Severity Index? So for the first one here, we have a 30-mile-per-hour collision, as is our standard, and we're stopped in a 5-centimeter distance. So as we did earlier, we've got our d sub s equals 1/2 times the velocity times the stopping time. So we've got to calculate that stopping time. That's the key here. So we've got the stopping distance in this case is 5 centimeters, so 0.05 meters equals 1/2 times our 13.4 meters per second times our stopping time. And so solving for that stopping time, we end up with 0.00746 seconds. So now we can use that to find the deceleration that we're experiencing. So that's going to be our velocity over our stopping time. So 13.4 meters per second divided by that 0.00746 seconds, we end up with a deceleration of 1,800 meters per second squared. So we have 3 sig figs. I'm just not bothering to write it in scientific notation. And so then we've got to divide that by the number of, to figure out the number of Gs. So the number of Gs, we're going to take that 1,800 meters per second squared. We're going to divide it by 9.81 meters per second squared. And so we end up with 183 Gs. So that's above our 30G criterion, but remember, what really matters is the exposure time. So that's where this Gadd Severity Index comes in. So now we're going to take that 183, We're going to raise that to the 2.5 power, and then multiply that times the exposure time, 0.00746. And so in this case, if we do that, we end up with a value of 3,380, which is well above our threshold of 500, which is shown by that line there on the previous graph. And so therefore, it looks like we're in bad shape on this one. In this next example, we're still at this 30 miles per hour, but now we have the seatbelt in the crumple zone we're taking advantage of to end up with a stopping distance of 1 full meter. So comparing that against the previous question, so we now have 20 times the stopping distance. So if our stopping distance is 20 times as long, then that means our stopping time is going to be 20 times as long, which means the number of G's we experience, because T sub S is in the denominator here, is going to be reduced by a factor of 20. So if we take our answer of 183 G's from before and divide that by 20, we end up with a mere 9.16 G's that the person is experiencing. So taking the stopping time from up above and multiplying it by 20, we get a stopping time of 0.149 seconds. So with this crumple zone and the seatbelt, we've reduced the number of G's, we've increased the stopping time. So now when we calculate our GSI, we've got 9.16 to the 2.5 power times the stopping time, 0.149. And so this time we end up with a GSI of 37.8, which is well below our 500 threshold. And so the G's alone are putting us in the survivable zone. And so hopefully the seatbelt, airbag do their job and keep us safe in this accident.